Okay, so right now we're looking at this PHET, and you got a little preview of it on the on-demand video, but I want to go a little slower here and do a couple things. So we would be using this in class. This is where I would actually use the dumb board, to be honest with you. This is where it's actually really good. So let's take a look here first. Let's look at, I call this see up here it says macro. Well, macro is a Latin prefix meaning like the big picture, like micro means small, obviously macro means large. So let's just take a look at a non-microscopic version of the properties of ionic compounds. So here's salt, we'll just call it table salt. And when you go to micro, you'll see it's sodium chloride. So let's just call it salt. Let's drop some in there. And what's happening is up to that top right, you're gonna start to see this word concentration. And what that means is how much dissolved salt is inside this water. The more stuff that dissolves, the stronger it is, the more concentrated it is. And another word for that is molarity, but we'll do that word in a couple weeks. So we say we have salt in there. We know microscopically in our mind, we'll show you soon, it dissociates. Means, remember, ionic, pretty strong bond, but can break apart because they're ions. So again, it's inside the solution. Now, what do we know about those properties? Will it conduct electricity? First off, it's soluble in water. It can dissolve in water. So let's put the conductivity tester in there and see what happens. Whoa, there's your bright light. Okay. So now, obviously, what causes it? It's if the sodium chloride was together in water, if the sodium chloride was liquid, it wouldn't conduct. You need the ions to be dissociated. Okay, they have to be dissociated. So right now they're dissociated ions, and those ions carry that electrical charge, that energy that travels through there. So I'm gonna watch this, and this gets a little bit advanced, but who cares? We're more than capable. I'm gonna remove some of this water. And what do you think will happen if I remove water? What do you think will happen to the concentration of salt? So think of the ratio, amount of dissolved salt to total quantity of water. Let's take a look. I'm sorry, I'm going to evaporate. Well, I want to evaporate the water this way. Notice that the light is getting brighter. See how the light's getting brighter? Why? Because the concentration of dissolved salt to water, it's not as diluted. It's more concentrated, it's causing more conductivity. Okay? So let me reset this. Let's do it like this. Drop all the salt in there, whatever. So we're starting with the same. There we go. I'm out. Okay. So now I boiled the water away, but what if I drain this? We'll put the conductivity tester in, it's set up as before. If I drain it, what am I removing? Am I just removing the water, or am I removing something else? The answer is you're removing salt and the dissolved ions. So let's take a look and see. I'm going to open up the drain. Watch the conductivity. Has it changed at all? Not at all. Because the ratio of dissolved salt to water is still the same. But wait a minute. Oops, hold on. Well, I want to let her remove more. That sucks. Okay. What if I remove all the water and salt? It won't conduct anymore. Okay. Reset. Let's add sugar in here. Now, what do we know about sugar? I will tell you sugar is made of carbon, hydrogen, and oxygen. Carbon is a nonmetal. Hydrogen is a nonmetal. Oxygen is a nonmetal. So it is a covalent compound. Let's drop that sucker in there. Sugar, 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 sugar. And some of it's dissolving, but it doesn't dissolve as much. But does it dissociate? Well, let's see. Are there any free ions in solution? No. Nothing at all. What about water by itself? Not conductive. It needs free-flowing ions. So let's add the sugar again. So this part here is just giving you a preview. It'll make more sense on the next part. Evaporate it. So what we're doing is removing the water. Oh, nothing's really happening. Okay, now the concentration of sugar went up because there wasn't much water left. Okay, go back to the salt for a second. Make sure that's at the bottom. Drop all that in. Oh, wait a minute. How come the ionic compound's not conducting? Because it's not in what? Water has to be dissolved to conduct. So the solid ionic compound, or the liquid for that matter, will not conduct. Let's add a little water. Whoa, geez. Oh boy. What's happening? I'm weakening the solution. Oh, ha, 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 ha. Okay. Boil this away. Oh, we have conductivity. Notice it's getting stronger. You can remove the sugar, it won't matter. Notice it's getting stronger. It's getting stronger. Eventually. Why is it like really strong? Because it's very highly concentrated with ions, right? There's the ratio of water that had, like the thing is, when we had a lot of water in here, not all this water was dissolving the salt. You had a lot of unoccupied water in here, so it's very dilute. You want the least amount of unoccupied or undistracted, undissolving water and high solute. But watch what happens when you go strong, 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 strong. All the water's gone. Whoop, solid ionic compounds don't conduct. Okay, let's get microscopic. And I'm going to stick with just these two. We could do other ones too. Same idea. Let's just keep it simple. Okay. So now let's take a look. Here's sodium chloride. Now watch this in the air. Now we have half a liter of water. Pause. Okay. What you see right here are those bricks that are built on top of each other. So here's a crystal lattice structure. Here's a crystal lattice structure. NaCl, NaCl, NaCl. The purple's Na, the green is Cl. You see how it's a crystal lattice structure? Predict what will happen the split second it hits the water. Let's see. Oh, do you know? What will happen? Boom. Oh my God, the water's going to explode. I've got sodium and chlorine in there. Holy crap. No. What do you have in there? Chill sodium and chloride ions that dissociated, not associate, dissociate, break apart in solution. So now we take the conductivity tester in here. Brilliant. Okay. But anyway, an ionic compound dissociates in water. And look at all this. All these guys move around will carry electricity all the way through. Okay. So therefore, they can dissolve in water. So I'm going to reduce the amount of, I'm going to boil the water. And what do you notice? Less water really having in it. Like, look here. Like some of this water is really not doing that much. So there's still, I can make this even stronger. And the light would get brighter and brighter and brighter and brighter until, what the? I know what's going on. It's an axe. What's starting to happen? There's less water. So what's going to happen? These guys are starting to what? Come back together. I wanted you to see that. Look at that. They're confused. There's not much water left. Do I go back with chlorine, chloride, and sodium, or do I go with the water? I'm confused. I don't know where to go. Look at this guy. Where do I go? They're still confused. Boom. So now you're back as a solid ionic compound. So what we did was, and this is why when you have salt water, when you boil the water away, this is the stuff that gets left behind. Okay, so I'm going to reset this. Now let's put sugar in here. Now sugar is a covalent compound. Now covalent compounds, their bonds are stronger. They have to share. They're not going to rip those bonds apart. They're not going to dissociate. But sugar, I will tell you, is polar. So it can dissolve in water, but it doesn't dissociate. So now watch this. Oh my Lord. Okay. Here's a bunch of sucroses. Here's a bunch of sucroses, and here's a bunch. So there's a crap load of C12H22O11s here, a crap load of C12H22O11s here, and the same thing here. So watch what happens when you put them in water. The compound stays together. But you see, like, this stays away from that. They just move around. So they still dissolve, but they still stay as one whole compound. The covalent bonds don't break. So let me ask you this. If water's polar, which it is, it's negative on the one end and positive on the other end, what do you think sucrose is? Do you think it's positive on one end and negative on the other, polar, or do you think it's non-polar? The answer is, you better get this right, it is polar, because polar likes polar. So these have charged particles, but the problem is, why don't they conduct? Because they do not dissociate. You need, like, hold on, pause this. you would need to see that little red guy right there be all by himself charged. And that's not going to happen. Why? Because if they do, they don't have a full outer shell. Their bond or covalent bond is strong. Okay? So now let's go to a more microscopic level. Okay, so now here's like a very microscopic depiction of water. And what you see right here is, this means sigma. That just means, it's just another Greek symbol. So the negative end is oxygen and the positive ends are the hydrogens, right? So these are polar molecules. And watch what happens when I put in the salt. Strongly positive, strongly negative. Bam. Oh man. Let's reset that. Do it again. We have dissociation. But notice they break apart because, again, they're cool with each other. Hey, we're good. We're stable. We break apart. Now we are surrounded by water. Take a look at the charges. Now, again, I guess it's hard to do this. But again, the positive Na is going to be surrounded by the negative ends of the water. And the chloride ends are going to be surrounded by the positive hydrogens of the water. So you see how that dissociates right there. Okay. So play that. There it goes. Okay, now we're going to drop the sugar in. So here's sugar, here's a C. So one of these is a C. I wish I could point. Okay. So this is it. There's two C12H22O11s right there. There's two compounds in there. What'll happen? Notice here, these guys, one compound here and one compound here. We talked about it before. They just have IMFs. They're now attracted to water. But notice the compounds themselves don't break apart because the covalent bond is really strong. So again, they can dissolve because they're polar. Okay, they can dissolve water because they have charged ends. And again, they get surrounded by the water, but notice they don't break apart. So do you see how large they are? They're very large. So if you go back to this, I'm going to add all the salt. Watch the concentration of the ions go up really high. Actually, we'll go here. It's better to, you can see it here better. Hold on. So the salt concentration is pretty high, right? So it goes to about there. What about the sugar? How much will that dissolve? Notice it's not dissolving as well because it's very large. And we'll get into that. Don't worry about that, but that's going to be next chapter. Larger molecules don't dissolve as much. Okay, and we'll get in. Don't worry about that yet. I just need you to understand the basics as it relates to their properties. Okay, again, if you have any questions off this, you guys should be really good with this. Ask at post the questions for virtual help desk, which we'll do on Friday. All right, that's it. Good job.